Hello, I'm J.D. Harrington, Public Affairs Officer at NASA headquarters in Washington, D.C. I'd like to welcome you to today's media teleconference where we will discuss the most recent science discoveries from NASA's Nuclear Spectroscopic Telescope Array, commonly referred to as NuSTAR. NuSTAR launched from an Orbital Sciences Pegasus XL rocket on June 12, 2012. After a short checkout period, NuSTAR started observing high-energy X-rays and higher resolution than any other space telescope before it. Now it enables astronomers to see the universe in an additional band of light, advancing our understanding of how galaxies form and evolve. Before we begin, a few topics to discuss. We have 4 panelists joining us today, and you can find the graphics the panelists will speak to by going to www.nasa.gov/NuSTAR and clicking on the link in the top right corner. Now, each panelist will give a short 3 to 5 minute briefing, and once finished, we'll then move to the question and answer session, accepting questions from media that dialed into the telephone bridge here, and those that submitted questions via Twitter using the hashtag AskNASA. Now, once again, the graphics can be found by going to www.nasa.gov/NuSTAR, that's NuSTAR, and clicking on the link in the top right corner. This media telecon will be limited to 1 hour. Today's panelists include Paul Hertz, NASA's Astrophysics Division Director at NASA headquarters in Washington, D.C. Fiona Harrison is also joining us. She's the NuSTAR Principal Investigator at the California Institute of Technology in Pasadena. Matteo Bachetti, an astronomer at the University of Toulouse, France. And Jeanette Gladstone, an astronomer at the University of Alberta, Canada. And with that, we'll get started. Paul?
Thank you, J.D. Today, NASA is announcing observations that NuSTAR has discovered the brightest pulsar ever seen. An object in the nearby galaxy M82 is brighter than we thought was possible for a pulsar. In fact, it's so bright that we assumed it must be a black hole. With NuSTAR, we have discovered that the object is emitting pulses of X-rays. We know that black holes cannot pulse, but pulsars can. So the discovery of the brightest pulsar ever seen is creating a challenge for our theorists. One of the things that NASA is very good at is space telescopes. We have large space telescopes like Hubble and Chandra, and we have small space telescopes. NuSTAR is one of NASA's small space telescopes. It is a small Explorer mission that was developed and is being operated by the principal investigator, Fiona Harrison, and her team. NASA has multiple space telescopes in order to provide different views of the universe. If you look at the first graphic labeled Hertz 1, we see 2 different views of the nearby galaxy M82. On the left is an image taken with the Hubble Space Telescope in visible light. This is what our eyes see. On the right is an image of the same galaxy taken in low-energy X-rays with the Chandra X-ray Observatory. It's clear that we're looking at very different phenomena in this galaxy when we're looking at it using different kinds of light. NASA will continue to develop different kinds of space telescopes with a broad range of capabilities so that astronomers can continue to study the most compelling questions of the universe. Today's discovery could have been made only with NuSTAR, the only telescope that can make these highly focused images using high-energy X-rays. To give you the details, here is Fiona Harrison, a professor at Caltech and the principal investigator of the NuSTAR mission. Fiona?
Okay, thanks, Paul. So, as Paul told you, today we're announcing the discovery of a pulsating dead star that's beaming X-rays with the energy of about 10 million suns. This dead star, called a neutron star, packs about the mass of the whole sun into a region the size of San Francisco. Yet this little Mighty Mouse pulsar packs the power of a much bigger black hole. This discovery is astonishing because no object like this has ever been observed to be even remotely this bright. Theorists didn't think that it was possible. The ultimate source of this object's power comes from the high rate at which it is feeding, or accreting, off matter from a companion star. High feeding or accretion rates are important for growing black holes in the early universe. This affects the formation of galaxies and structures in the universe, and studying objects like this helps astronomers understand this important process. So if you scroll down to Harrison 1 on the web page, this image shows you a visible light picture of the galaxy called the Cigar Galaxy, or otherwise known as M82. This is the galaxy in which this object was discovered by NuSTAR. The purple dot shows you the location from which NuSTAR observed intensely bright X-rays during a 2-week-long observation. Due to their brilliance, X-ray objects like this one, found in nearby galaxies, not in the precise center, but offset from the nucleus, the precise point about which all stars and dust and gas revolve, these are called ultraluminous X-ray sources. Until now, astronomers have believed that they're all powered by rapidly feeding black holes. The reason for this is that black holes, due to their mass, can power very bright X-ray light bulbs. So why did we think these ultraluminous X-ray sources are powered by black holes? Well, the energy source that powers bright X-ray sources is gravity. Matter falls onto a very dense, very compact object. The more massive the object and the more matter that falls on, the more power that it can produce. So if you scroll down to the graphic Harrison 2, this shows you the mass range of dense objects that can power these X-ray light bulbs. On the small side, stellar mass black holes, neutron stars and white dwarfs, these all form as remnants of the death of a single massive star. We know that all these types of objects exist in our galaxy, not in the precise middle, as I said, but scattered around in the regions where massive stars live and die. On the big side, the very right-hand side of the graph, are supermassive black holes. Now, these are different. They reside in the very hearts of galaxies, and they are formed not instantaneously from the explosion of a single star, but by gorging on material for very long times, a good fraction of the age of the universe. In the middle, underneath that question mark, are what we call intermediate mass black holes. Now, do they exist? Well, we don't know, but these ultraluminous X-ray sources are considered good candidates that may fill this mass void. Why? Well, as I said, the more massive an object and the more it eats, the brighter it is. There's a limit to any object's food supply, of course, so the very brightest X-ray sources are suspected to harbor black holes. Think of it this way. With a given food supply, the brightness depends directly on the mass. So if a 1 solar mass neutron star produces 50 watts, a 100 solar mass black hole will produce 5,000 watts. That's the difference between a nightlight and a spotlight. So NuSTAR found this bright spotlight in the galaxy M82, and immediately we thought, this is so bright, it's a large black hole. Now, if you look at the graphic Harrison 3, this is an artist depiction of what we were quite sure the object looked like. A black hole, shown on the left, feeding off matter from a normal star, which is shown on the right. And even with a black hole 50 to 100 times the mass of the sun, the feeding rate implied is pretty extreme. But then we discovered that rather than just being extreme, the object is in fact astonishing. I'll turn it over to Matteo Bachetti to tell you how our black hole theory was destroyed. Matteo?
Hi, thanks, Fiona. So how did this happen? I was looking at this source, and I was, of course, sure that it was a black hole like everybody else. And I was particularly interested in how the signal, the X-ray signal, changed in time, because seeing how this signal changes in time, sometimes you have the possibility to measure the mass of the black hole. But then I realized that the signal was not only changing, but it was pulsing. And that's another story. You can see it on figure Bachetti 1. These are the NuSTAR data when the pulse is on and when the pulse is off. You can see a clear difference already in this picture. If you had X-ray eyes, that's probably what you would see. Well, as I was saying, black holes cannot pulse. The only way to produce a pulse like that, so stable and also so fast, is to have a rotating neutron star. You can see how this works in the video, Bachetti 2. There is matter that is captured in the gravitational field of the neutron star and tries to fall on the star. But then these stars have tremendous magnetic fields. And this magnetic field is able to capture the matter before it falls on the surface of the star and concentrate the fall of the matter onto two very bright spots. These two hot spots can reach like 10 million degrees or more. So you can think of them like huge X-ray lamps. These lamps of X-rays, as the star rotates, are only visible by us when they're pointing at us. Think about it as a big X-ray lighthouse. And in a lighthouse, what you see is a pulsed signal. And that's exactly why in these systems we observe an X-ray pulse. That's why also these systems are called pulsars. Well, there are many known pulsars in our galaxy also that work with this mechanism. The only problem is that they're never so bright, not even close. So why this one can manage to be so bright is still under investigation because, well, until now, nobody thought it was even possible. I'll pass the word to Jeanette Gladstone from University of Alberta to give a wider look at this discovery.
Thanks, Matteo. Thanks for the introduction, and also thanks for the team for inviting me. I wasn't actually part of this project, but I do work on these ultraluminous X-ray sources, and I have worked on neutron stars in the past. And so I found this really interesting result, and it's great to see a small telescope making such big discoveries, result that's going to lead to much discussions in many areas of astronomy. Ultraluminous X-ray sources have been a mystery since they were first observed, really, but the first thing that we all agreed on, as Fiona said earlier, was that we thought these things must be black holes due to the brightness of them. The only question that we had left was what kind of mass were they? How much did they weigh? Were they stellar remnant black holes? Were they things that were extreme systems, so the size of black holes that we find in our own galaxies, but eating at much more extreme rates? Or were they these mysterious and elusive intermediate mass black holes, the missing link between the stellar remnants and the supermassive black holes found in the center of galaxies? Well, recently the community's been settling on the idea that the majority of these are stellar remnant black holes in a new extreme accretion rate, which is a very exciting discovery, and it kind of pushes the boundaries on what we thought was possible for accretion, for how these objects feed. And this was supported by a paper that came out last year by a group led by Liu et al., and also by a paper that comes out in the same issue of Nature by a group led by Moch. But the galaxy M82 is actually making us stop and think about these things. So if you go to figure Gladstone 1, you'll see a zoom in of the area in M82 that holds this ULX that we're talking about today, this ultraluminous X-ray source. And you'll see that there's two sources labeled there. X1, which is the brightest X-ray source in this galaxy, and X2, which is the second brightest. So X1 was in the news recently because recent X-ray analysis of that source has shown that it may be one of these intermediate mass black holes. The authors suggested that this object weighed about 400 times the mass of our sun. So it's definitely in that intermediate mass black hole range. Now, we're looking at M82X2 here today, and this object isn't even a black hole at all. So this source is even more extreme than anything we'd previously considered. This is a neutron star not only feeding at black hole rates, but feeding at rates that are extreme for these stellar remnant black holes. So this is quite exciting. It's definitely going to be a surprise to the community that studies these ultraluminous X-ray sources, but not just that community. It's going to have wider impact as well. The sources in M82 are really kind of challenging theories and pushing our limits and understandings of ultraluminous X-ray sources, but also neutron star physics. And it's also going to give theorists a challenge in trying to explain their new ideas on how neutron stars and black holes can feed at these rates, an area that we call accretion physics. This can help us explain the rapid growth of massive black holes in the early universe. It can help us understand more about the formation of supermassive black holes. And there are actually links between the supermassive black holes found in the centers of galaxies and the galaxies they reside in. And so it's thought that if you can find out more about the formation of one, you can find out about the formation of the other. So this could tell us more about the formation of galaxies as well. So this is really an exciting result, showing new possibilities not only for areas of research in ultraluminous X-ray sources, but also for other fields in astronomy. So I'd like to thank the team again for inviting me along today, and I'd like to pass it back to JD.
Thanks, Jeanette. And with that, we'll start the question and answer session. We have several reporters on the telephone bridge today, and as such, we'll need to limit everyone to one question with one follow-up. I'm sure we'll be able to get around and for additional questions. We'll start from the beginning, and Yumi, our operator, should identify you. If not, though, I ask that you identify yourself, your media affiliation, and then direct your question to a specific panelist if possible to eliminate any confusion. Now, for those dialing in, you can push the *1 keys on your telephone to be placed in the queue. And to use Twitter, send your questions to #AskNASA. And with that, we'll begin. Yumi?
Thank you. As a reminder, if you'd like to ask a question, please press *1 and record your name. First question comes from Bill Harwood from CBS News. Your line is now open.
Thank you very much. And I apologize if I missed something. I want to make sure I understand the relationship between ultraluminous X-ray sources and intermediate black holes, because I'm not sure I'm getting that. What is the connection on that nice graph that showed the one that nobody understands what they are? I just don't understand where these things fit in. Thanks.
Okay. Jeanette, do you want to take that, or shall I?
I'm happy to take it, yeah. Thanks for the question. So these intermediate mass black holes were suggested as a way to kind of have a stepping stone between the stellar remnant black holes that we see in our galaxy and the supermassive black holes in the center of galaxies. It gives you a way to kind of bridge the gap between them, but it also gives you a way to form the supermassive black holes found in the center of galaxies. Now, as Fiona said, you've got this. We know from observing sources that we've seen in this galaxy and in other galaxies, the brightness of these sources scales with their mass, scales with their weight. So if you increase in luminosity, if you look at X-ray sources in the sky and look at them as they increase, you go through neutron stars, through stellar mass black holes, and then we seem to have a gap, and then you get to supermassive black holes. They're the brightest things that you see. And so it was thought that if you get something that is intermediate in luminosity, intermediate in brightness, then it could also be intermediate in mass. So it might be these objects that could help us explain how to make supermassive black holes. Does that make sense?
Yeah, and so let me clarify a little more. So what is astonishing about this result and a number of other recent results is we look at these bright X-ray light bulbs in nearby galaxies. We call them all ultraluminous X-ray sources because they're sort of intermediate in brightness between what we would normally think of as a neutron star and a supermassive black hole. So this is what led people to believe they were all the same thing, maybe intermediate mass black holes. And this has been turned on its head by the discovery that one of them is in fact a pulsar, which contains a neutron star, not a black hole at all. So this is kind of overturning our ideas and making us wonder how something that's, this little pulsar can be so mighty, so bright. And that's a challenge.
Well, Fiona, I'm sorry, but that is exactly my question. I understand this is a new class of particle, but star or object, I should say. But is that something that serves as a candidate for this intermediate mass object, or is this something completely different? That's what I'm not understanding.
Okay, yeah, so the one that we are talking about today, the one labeled X2 on Gladstone 1, isn't a black hole at all. It contains a neutron star, which is the dead remnant that's left over when a massive star explodes. Now, what may be confusing you is the one labeled X1, which is in the same galaxy, is a candidate to be an intermediate mass black hole. So right next to one another, almost the same brightness in this image, we have an intermediate mass black hole and this little Mighty Mouse pulsar. That's really amazing. Does that answer your question?
Yes and no. I mean, really my problem is, does the new object that you guys have found, assuming this is a category of some sort, and you may find other examples at some point, do these objects serve that stepping stone role between stellar mass black holes and supermassive black holes, or do you still need the intermediate mass black holes, and these are in fact a totally different phenomenon? Thanks.
The intermediate mass black holes are a different phenomenon than the pulsar that we are announcing today. Now, what we see in the galaxy is 2 points of X-ray light that are about the same brightness. And so one might think, oh, they're the same thing. But what we're announcing is that one of them contains not a black hole, but a pulsar, so is not this missing link. It's not an intermediate mass black hole, even though it looks like one. And that is really the discovery.
So
Thank you.
Sorry to jump in. I just wanted to clarify and add on to the mass estimate. So this is basically saying that X1 that you see there is about 400 times the mass of our sun, whereas we're saying that X2, or rather the team who's announcing this today, saying X2 weighs about 1 to 1.5 times the mass of our sun. So these are really different sized objects.
Thanks. This is JD, and once again, if you have a question on the telephone bridge, push the *1 key. And if you'd like to ask a question and ask NASA, just send it on your Twitter to #AskNASA. We do have a question here from the social media. What is the spin rate of the new bright pulsar in M82?
I can take this. It's 1.37 seconds to complete a rotation, so 0.7 rotations per second.
Okay, and we have a second question here on social media. Is this pulsation from M82X2 a transient phenomenon? Was this not observed with Suzaku HXD?
Yeah, it's most probably a transient phenomenon because we haven't found evidence for it in past observations for not only Suzaku but many other satellites. And also in our observations, there's at the start of the observations, we don't see pulsations. Pulsations start afterwards, and that's actually a very interesting feature of this pulsar.
Yeah, and let me clarify a little more here. The new thing about NuSTAR is that it's the first focusing high-energy X-ray telescope. So unlike the Suzaku HXD, which cannot resolve the different sources in this galaxy, so it can't tell the difference between X1 and X2, NuSTAR is the first high-energy X-ray telescope that can. So it's the first time we've been able to separate out the high-energy X-ray light from these two sources and study them. And we know that this source X2 is sometimes very bright and sometimes very dim. And so it does vary, and we think that when it's bright, that's when you can see these pulsations, but it's really the new kind of X-ray eyes that NuSTAR has that has enabled this discovery.
All right, we're going back to the telephone bridge. Yumi?
Our next question comes from Mike Wall from space.com. Your line is now open.
Okay, thank you guys for actually doing this. This is sort of, a broader question about just kind of medium-sized black holes. Could you just sort of take a step back and sort of say what you think is known now about medium-sized black holes? Do we really think that they exist? Are they still hypothetical objects? Does the astronomical community, are they pretty sure that they exist? It's just hard to confirm them. Could you just say a few words about medium-sized black holes and what kind of where the sort of search for them is right now, and what this new finding means for that search?
Okay, Jeanette, did you want to take that, or shall I?
Yeah, I'll take it. It's been suggested that there should be these medium-sized, these intermediate mass black holes out there, and most ideas on how to make supermassive black holes require these intermediate mass black holes. The problem is that they're very difficult to find. So far, there are only maybe 2 strong candidates that we have for these intermediate mass black holes, and one of them is M82X1, which you can see in the figure Gladstone 1 there. This new result doesn't necessarily impact the field of intermediate mass black holes. It doesn't necessarily impact the study for intermediate mass black holes. It does shake up the community that look at ultraluminous X-ray sources. And those who are looking at ultraluminous X-ray sources are usually looking for intermediate mass black holes as well. So it will make us stop and think and look for new options to explain these strangely bright objects. But as it stands, intermediate mass black holes are very hard to find.
Yeah, but they are, as Jeanette says, they are very important because we believe that they had to exist in the early universe to be the seeds from which the very massive black holes grow. And so you look at, how do you look for them? Well, one way is to look for these very bright X-ray sources. And here X2 has really tricked us. It tricked us into thinking it was perhaps an intermediate mass black hole where it actually isn't.
Okay, we're going back to the social media sphere here. Got another question. Do we have any similar objects in our own galaxy?
Sure, I can take that. Yeah, there are similar objects in that there are pulsating neutron stars in our galaxy. And we think they work similarly to this new source. The only thing is they're much dimmer, more than 10 times fainter. Even the very, very brightest ones are more than 10 times fainter than this. So there's probably some new physics going on here, some new process that we don't yet understand that can make this so bright.
All right, thanks. Once again, if you have a question, you can push the *1 key on your phone on the telephone bridge, or you can send your question via Twitter to #AskNASA. Another question here. How difficult was it to make this observation with NuSTAR? How were these rapid observations taken?
Well, they were not really rapid observations. It was a single observation in which you could measure the variability of the X-ray signal in very short time scales. And I don't think it was a very difficult observation for NuSTAR, because NuSTAR is just extremely good at doing this kind of observations.
Yeah, and I'll say that what's interesting is this is an example of serendipitous discovery, because we were looking at this cigar galaxy not to study these ultraluminous X-ray sources, but to follow up on a supernova that exploded there. And so that's why we stared at the galaxy for so long. And these sources just happened to be in the field of view, to be visible in the same image. And so Matteo was looking at them, searching for signatures of massive black holes, and instead found this pulsing off and on. And so it was really a surprise. It took us a little while to believe it, because it was so astonishing.
We have a question from Daniel Cleary from Science Magazine. Your line is now open.
Hi. I just wanted to ask, this very, very luminous pulsar, have you got any theories about what process could be creating its extreme brightness?
Matteo, do you want to take that, or shall I?
It's okay, I can take it. There are some theories. It's at this stage they're still little nebulous because such luminosities were not really thought of a lot. But there are some ways to overcome the limits that usually exist in the luminosity of these objects. And in pulsars, there are several things that might happen. One includes the fact that these stars have a very strong magnetic field, and this in some way might happen to eat more matter per unit time, let's say, and so produce a very high luminosity. Another thing that might happen is that as the fall of the matter is concentrated in very small areas, it might somehow be easier for this matter to fall undisturbed on the surface, so at very high velocities, very high rates, than in black holes, when the fall of the matter is more homogeneous. I don't know the amount of detail you were asking for.
No, that's fine.
Yeah, I will say that it's a puzzle for theorists, because there's a very famous paper that predicts the brightest that you should be able to see a pulsar at, and it's more than 10 times fainter than this one. So I think there will be new theories that come out of this observation.
All right, we're going back to the Twitter sphere. What was the spectrum for M82X2 in this observation? What physical model was most successful?
It's quite difficult to determine because there are these two very bright sources close to each other, and NuSTAR cannot resolve them spatially. Okay, that's why we used also other satellites to help disentangling between the two bright sources. And so obtaining a spectrum that has only X-rays from our source is actually quite tricky. We tried somehow, but for now we don't have a result that is ready to be discussed.
Okay, another Twitter question. Does the accretion rate for the pulsar suggest that it is accreting from a rich environment, perhaps a nebula or multiple stars?
It's not needed. The standard way these kinds of objects accrete, that is, feeding off a companion star, can reach these rates. The problem of obtaining high luminosities is closer to the compact object, not the rate at which these objects can attract matter from the companion star.
Okay, once again, if you have a question on the phone bridge, you can push the *1 key to be put in the queue. And for Twitter questions, use the hashtag AskNASA. Back to Twitter right now. How does this NuSTAR finding distinguish between far-away and close-up X-ray sources? How does NuSTAR distinguish between far-away and close-up X-ray sources?
So that's a very good question. The reason that we can tell the distance to these X-ray sources is because they lie in this galaxy the cigar galaxy, and we know how far away that galaxy is. And we know both X1 and X2 are embedded in this galaxy because in the low energy part of the X-ray spectrum, for low energy X-rays, we see those X-rays made dimmer because they are absorbed by the dust and gas in this galaxy. So we know the sources are in this galaxy, and we know the distance to the galaxy.
All right, thanks. We have another Twitter question here. How many other objects like this one are out there? Is this one of a kind?
Matteo, do you want to take that?
Well, that's the question, right? Now we found one, and it's possible that this one is an oddball, or it might be possible that there are others. Of course, the next step is to look for pulsars in other ultraluminous X-ray sources.
Right. So this is something we don't really know, as Matteo said, and NuSTAR is going to be searching for more.
Okay. Once again, if you have a question on the phone bridge, use *1, and for Twitter, use #AskNASA. We'll stand by for just a moment for the next question. Stand by. We have a question that came in via email. Can the object accrete sufficient mass to collapse into a black hole? If this may happen, any idea on the time frame?
That's a really good question, and in fact, that is a prediction. If the pulsar is accreting matter or eating matter at the rate that we think, it shouldn't last that long before it turns into a black hole. Now, that won't happen in our lifetime, but it will happen on a relatively short time scale in terms of the age of this galaxy and the age of the other sources in it.
Do we know what size the black hole would be?
Well, approximately, when something becomes more than a few times the mass of the sun, it can no longer be a neutron star. It collapses into a black hole. So it would be a few times the mass of our sun.
I'm sorry, now we got a question from Twitter, rather generic. How well is NuSTAR doing after 2 years in space, and what's next to come for it?
Well, so NuSTAR has just finished what's called its baseline mission. That was the mission 2 years, and has just been turned over to the community for 2 years, where anyone in the world can propose to look at something with NuSTAR. That's called a guest investigator program. And so NuSTAR is very healthy. The satellite is still working as well as it did the day after it launched. And we hope that there will be many more years of guest investigator programs where people from around the world can use this telescope.
All right, one last time. If you have a question from the telephone bridge, *1 on your phone, and Ask NASA. We'll be closing down in just a moment. Stand by. All right, I guess that's going to do it for today's News Telecon. I'd like to thank the panelists and our operator, Yumi, for their time today. I asked the panelists to stay online for just a few minutes for post follow-up. And for the listeners, our panelists will stay behind and answer any other questions that pop up on Twitter's hashtag AskNASA forum. If you joined this telecon late, you can listen to it again by dialing 1-800-839-1248. That number again is 1-800-839-1248. To find out more about these findings or for more info on any of NASA's many programs and projects, visit us on the web at www.nasa.gov or via our many social media venues such as Facebook, Google+, Twitter, YouTube, and many more. Once again, thanks for joining us, and have a great day.
Thank you for your participation. You may disconnect at this time. Speakers, please stand by for the post-conference.